the recording. Okay, let's get started. Nice to meet you all, and I'd like to welcome you to our P&S course. By the way, you can see my screen, right?
Yes.
Okay, thank you. And this is the first lecture for the P&S course entitled Understanding and Designing Modern NAND Flash-Based Solid-State Drives, in short, P&S Modern SSDs. And I'm Ji-Sung Park, a senior researcher and lecturer at Safari Research Group, led by Professor Ono Mutulu. Okay, so before we get into the course, let me briefly introduce who we are. So we are the Safari Research Group led by Professor Ono Mutulu, again, a full professor at ETH Zurich since September 2015. And Professor Mutulu is also a faculty member of Carnegie Mellon University, where he held a Strecker professorship before joining ETH. You can find his research and project in more details on his webpage. And he's actively working in both research and teaching in a wide area broadly related to computer architecture, including memory and storage systems, hardware security, and bioinformatics, and many more, many other things also. And the Safari Research Group consists of around 40 researchers who are actively working on top-notch research projects with a motto, think big, aim high. And in the group, there are currently 8 postdocs, 13 PhD students, 7 master's students, as well as 6 affiliated researchers from various institutions and companies. If you are interested, I would recommend you read our newsletters that we publish twice per year currently. And there we share our recent research and publications, as well as some interviews with our members about their work. And for this P&S course, we have 3 supervisors. First, me, the lead supervisor, and I have worked as a postdoc and lecturer at Safari Research Group since September 2019. I earned my PhD degree from Seoul National University in South Korea, and my research interests lie in computer architecture, memory and storage systems, and system security. And you can get more information about me from my website if you are interested. And luckily, we also have 2 very experienced supervisors. First, Dr. Mohammad Sadro Sadati is a senior researcher who recently joined the Safari Research Group. Before joining the group, he worked at IPM at Iran, which stands for the Institute for Research in Fundamental Sciences. He earned his PhD degree from Sharif University of Technology. And his research area spans energy efficient GPUs, solid state drives, processing in memory, and machine learning. Second, Rakesh Nadik is a PhD student of the Safari Research Group, and he has started his PhD program at ETH from this semester. Before joining the group, he worked at Samsung Electronics India as a senior staff engineer for 7 years. He earned his master's degree from UC Irvine, and his research interests lie in computer architecture, memory system design, multi-core architectures, near-memory processing, and non-volatile memory. Let's get into the course. Please interrupt me if you have any questions. So this is the course catalog page for our P&S course, which I believe you have already read. But let me summarize the course with some keywords and key sentences. As the title suggests, this course aims to understand and design modern NAND flash-based SSDs. So NAND flash memory is a de facto standard in architecting a storage device in modern computing systems, from mobile systems to enterprise server systems. Personally, I believe NAND flash memory has enabled various technologies that we are now using every day. For example, it is very hard for me to imagine how we could implement our smartphones without NAND flash chips. I also clearly remember the day I first installed an SSD to my desktop. And at that time, so booting a PC with only a hard disk drive, or HDD in short, took hundreds of seconds, while it is very hard to imagine, right? And while now the booting takes only around 10 seconds at most. And it was indeed kind of one of the most impressive moments. I directly felt the advance of technologies in computer systems. And NAND flash-based SSDs have become more important also in high-performance computing systems, such as data centers, to efficiently deal with large amounts of data processed in this data explosion era. Unfortunately, NAND flash memory has various unique characteristics, such as the erase before write property, limited lifetime, and large operation units, which do not exist in traditional HDDs. So it is critical to design efficient SSD firmware, commonly called the flash translation layer, or FTL in short, which is responsible for many internal SSD management tasks, such as address translation, garbage collection, real labeling, and I/O scheduling, in order to provide high performance, long lifetime, high reliability, and backward compatibility of the SSD, while hiding the unique characteristics of NAND flash memory. So in this course, basically, we will build a practical SSD simulator by extending MQSIM, a state-of-the-art simulator for high-end SSDs. Okay, in this course, we will introduce the necessary background for you to understand how a modern NAND flash-based SSD is commonly organized and operates, which I hope allows you to learn fundamentals and challenges in designing modern SSDs. We will also introduce some widely adopted approaches and recommend related papers good to read, which can help you get familiar with new research proposals. Most importantly, you will work hands-on in extending a state-of-the-art SSD simulator, analyzing I/O workloads, optimizing SSDs, and evaluating SSD designs, and so on. So let me introduce a brief but a little more detailed background on our topics. A modern SSD is quite a complicated embedded system that consists of multiple cores, hardware controllers, DRAM, and multiple NAND flash packages. So this is a top view of a PCB of a Samsung SSD for enterprise servers, which has about 960 GB capacity. You can see 4 NAND flash packages there, but in fact, there are other 4 packages at the bottom side of the PCB. So each package has a 128 GB capacity. And it also has low power DDR DRAM to store metadata that is necessary for efficiently managing the underlying NAND flash chips. And typically the DRAM capacity is 0.1% of the SSD capacity, meaning that, for example, this SSD whose capacity is about 1 TB has a 1 GB LPDDR DRAM. Finally, the SSD has a powerful SSD controller that has 3 ARM Cortex cores and multiple hardware flash controllers that are responsible for request handling, error correcting codes, or ECC in short, data randomizing, and data encryption. So why is a modern SSD so complicated? It is because an SSD needs to provide the backward compatibility with traditional HDDs. An HDD is usually composed of a bunch of sectors that are smaller than file system blocks. For example, the basic sector size is 512 bytes, whereas the default block size of widely used file systems, such as ext4 in Linux systems or NTFS in Windows system, is only 4 kilobytes. And HDDs support overwrites, meaning that if you want to update the content of a sector, you can simply rewrite the sector with the new data. However, as I explained, NAND flash memory has many unique characteristics that do not exist in HDDs, and here I listed only representative ones. So let's take a look at some of these characteristics very briefly. First, NAND flash memory has large operation units, meaning that it reads and writes data at page granularity. The page size of a modern NAND flash chip is typically 16 kilobytes, while only some latency optimized chips have 4 kilobyte pages. So except for such latency optimized NAND flash chips, the minimum I/O units of NAND flash memory is 4 times larger at least than the default block size of widely used file systems, which introduces several new technical problems. So we will discuss this issue later in a background lecture. And second, a page needs to be first erased before programming, which is commonly called the erase before write property. So in fact, for sure, you can issue a program command with new data on any pages in the SSD. But if the page has not been erased previously, you cannot guarantee that the new data is correctly returned to the page. So to avoid any data loss or data corruption, we must perform an erase operation before programming new data on a page. Third, NAND flash memory performs an erase operation at block granularity, and a block in modern NAND flash memory consists of hundreds or even thousands of pages. So such a large number of pages must be erased at the same time. So these three characteristics combined to each other make it very inefficient to perform in-place updates or overwrites for NAND flash memory. So suppose that you want to update the content of a programmed page. Then you need to first erase the page due to the erase before write property. But since the erase granularity is a block, so you need to erase the entire corresponding block that contains hundreds or thousands of pages along with the page you want to update. If some other pages in the block are valid, meaning that the user can access the pages in future, we need to first read out all the valid pages in the block and temporarily store them somewhere, for example, in DRAM. And then finally, we can erase the block, update the page, and write back the temporarily stored data again. So you can imagine that this takes a very long time. So modern SSDs commonly perform out-of-place writes, meaning that they always write new data to a new page that has been previously erased, and perform garbage collection to reclaim the page that stores the old data in order to use the page for future write requests. So another important characteristic of NAND flash memory is that it has limited endurance, meaning that a flash cell becomes unable to store data reliably after experiencing a certain number of program and erase operations, or P cycles in short. And this limited endurance problem becomes more serious as manufacturers adopt aggressive multi-level cell techniques that store multiple bits in a single memory cell, thereby increasing the chip density without semiconductor process scaling. For single-level cell NAND flash memory, for example, where a single cell stores only 1 bit, the maximum number of P cycles was larger than 100K. However, in QS NAND flash memory, where each cell stores 4 bits, after less than 1K P cycles, a page can no longer store data reliably. So a modern SSD requires a proper lifetime management, such as rail leveling, that aims to evenly distribute the P cycles across all blocks in the SSD. And this is necessary because if only a small portion of blocks, let's say 10% of the total blocks in the SSD, becomes unable to use due to high P cycles, it may also make SSD unusable, since the SSD cannot provide the specified capacity any longer. So it is really important to keep the P cycle variation across the blocks as low as possible to maximally use the potential endurance of underlying NAND flash chips. So to deal with such unique characteristics of NAND flash memory, a modern SSD implements a sophisticated firmware, commonly called the flash translation layer, or FTL in short. Basically, by using NAND flash chips, an SSD needs to provide a storage device view to the operating system as if the storage device consists of contiguous data blocks, each of which is 4 kilobytes in size and can be overwritten. To this end, the FTL performs various internal management tasks, such as address translation and garbage collection for out-of-place updates, lifetime management, such as rail leveling, reliability management to hide the error proneness of NAND flash memory, and I/O scheduling for maximally exploiting the potential performance of NAND flash chips. And as you can imagine, all these tasks significantly affect the performance, lifetime, and reliability of the SSD. So there are many research topics there. So in order to optimize an SSD, one needs to comprehensively understand the design of underlying NAND flash chips, as well as various internal management tasks necessary at the FTL level, and OS and workload characteristics. And optimization at one level may affect or be affected by the efficiency of optimizations at other levels. For example, even if you come up with a very nice idea and implement it at NAND flash architecture level, it may not be able to improve any aspect of the SSD at all, unless the FTL efficiently leverages the new feature. So in SSD optimizations, we need an SSD simulator that can accurately model various functionalities and components of an SSD, unless you are willing to put huge effort into prototyping a real SSD. Okay, so far I discussed the topics that we will work on in this course. So before I move to the course of logistics, do you have any questions? Okay, good. So we will carry out this P&S course in 2 phases. So in the first phase, you will learn fundamentals of NAND flash memory and NAND flash based SSDs through 3 or 4 background lectures on the organization of NAND flash memory and NAND flash based SSDs, NAND flash operations, and SSD management tasks, which I will deliver in the first 3 or 4 meetings, excluding this one. And during the first phase, we will also ask you for reading some important papers related to the topics discussed in each background lecture. And in the second phase, each of you will be asked to extend the MQSIM with one of advanced features widely adopted in modern NAND flash-based SSDs. And all of them will be covered by the background lecture. And please note that we will provide the backbone course for the features, the implementation of features to you. So I believe your workload is not so huge, hopefully. So please do not worry about in advance. And we expect this P&S course to allow you to improve your knowledge in computer architecture with a focus on modern storage systems, technical skills that are required for good research, and critical thinking and analysis. We also hope this course can provide you with a chance to interact with a nice group of researchers, get familiar with the key research directions, and improve technical presentation of your work. So basically, we expect you have taken digital design and computer architecture or equivalent courses as a prerequisite and are be familiar with the C++ programming. But I don't think the later one is truly important, as I believe you can learn the programming language itself during your hands-on work. And more importantly, we expect you are interested in computer architecture and systems for sure, and discovering why things do or do not work, and solving problems and designing an efficient and practical system. And this was the introduction of ourselves and our course. And we would also like to know your background and interests. So there is a Home of Zero at our course webpage that I'm going to introduce soon, and that asks you for providing information about you. So the due date is 5th October, and please submit the homework in the Moodle system. And basically, you are supposed to attend all the meetings and study the learning materials that we will announce before or after each lecture. And each of you will work on hands-on projects on one of the topics we will suggest at the end of the first phase. And I hope you actively participate in the project, and any question, discussions about your thoughts and ideas would be welcome in our meetings. And again, our primary goal is to help you learn as many things as possible from the course. So please don't hesitate to contact us if you have any questions or difficulties in the project. And if your work is really good, hopefully, you may get it published and keep working with us. And this is our course website, and please check it regularly. And there we will upload useful information and learning materials. And we will also have a Moodle for Q&A, but we can also discuss via emails or face-to-face or even a Glip channel for more active interaction. And these are the first learning materials for today's meeting. So first, as required materials, please read the research paper that describes MQSIM, published in a prestigious storage conference named Usenix File and Storage Technologies, or Usenix FAST in short, in 2018. And we also expect you to download the MQSIM source code from the repository and analyze its current organization as thoroughly as you can at this moment. As recommended materials, we strongly encourage you to watch 2 recordings of last year's computer architecture lectures for master's students. There, Professor Mutlu delivered a very comprehensive lectures on challenges and optimizations for NAND flash-based SSDs in the reliability perspective, and why simulation is important in computer architecture research with a focus on memory systems, respectively. Basically, we will meet every week, and the next meeting will take place next Wednesday. And as I explained, in the first 3 or 4 meetings, I will deliver background lectures. And after that, in each meeting, we will briefly discuss your progress in the previous week and have Q&A sessions for any difficulties in the previous week and directions for next week's. In the final meeting, or even before, each of you will also present your ongoing work or results. Okay, so this is all I have prepared, and I hope we make an exciting course that allows you to learn something important in your major. Okay, so do you have any questions? Okay, I take that as a sign that everything is really quite clear, right? Okay, so thank you for joining, and I will send the links to our homepage where you can find everything mentioned in this meeting. Okay. Okay, thank you for joining, and see you next week. Take care.
Thank you, Jason. Bye.
Bye.
Thank you. Bye.
Goodbye.